Have you ever really stopped to think about what's happening inside your computer when you say click a mouse? It's not magic, not at all. It's pure logic, a kind of beautiful, intricate dance of data moving at speeds that are almost impossible to wrap your head around. In this explainer, we're going to pull back the curtain on the code that powers our digital world and, really uncover the story that's hidden inside. Okay, so you look at this and yeah, it probably seems like a completely incomprehensible wall of text, right? But believe it or not, this isn't just a bunch of code. It's actually the architectural blueprint for a digital superhighway buried deep, deep inside your devices. Every single thing, every pixel on a video, every character you type, it all has to travel this highway. So our mission today, we're going to follow one tiny packet of data and see what its journey is all about. So let's meet our hero for today, a single, humble packet of data. Now, this packet could be anything. It could be a piece of a game's texture, a few words from an email, maybe a frame of a video you're streaming. All it wants, its entire purpose, is to get from point A to point B. And that whole journey kicks off with one simple, urgent request. I need to move. Now, for our packet to move at, the speed of light, it uses this incredible shortcut called Direct Memory Access, or DMA. Just think of your computer's main processor as a super busy downtown city center. Well, DMA is the express lane, the bypass that goes around all that traffic. It lets things like your graphics card or your network adapter talk directly to memory without clogging up the main roads. And the code we're looking at, that's the blueprint for one of these express lanes. So how does our little packet even get onto this superhighway? Well, it all starts when some component, let's say your network card, sends out a little signal. In the language of our blueprint, this signal shows up on something called an input wire, which is labeled, pretty simply, request. The second that signal flips on, the system knows, hey, I've got a packet waiting. And just like that, its journey has officially begun. All right, so our packet has basically raised its hand. But it can't just merge onto the superhighway whenever it wants. Come on, that would be chaos. Just like any busy intersection, there's gotta be a system to manage the flow of traffic. It first needs to get permission from the gatekeeper. And this gatekeeper is a piece of logic called the arbiter. Honestly, the best way to think of it is as a digital traffic cop. You could have dozens of different parts of your computer all yelling, me, 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 trying to send data at the exact same time. The arbiter's job is to look at all of them and in a fraction of a nanosecond decide who gets the green light. So how on earth does this traffic cop decide? Well, it basically follows one of two rulebooks. The first is called strict priority. It's simple. The highest priority request always wins. Super efficient, but it means a lower priority packet could get stuck waiting forever. The other option is round robin, which is way more fair. Everybody gets a turn in a nice, orderly cycle. No one gets left behind. And this right here is what's so brilliant about this code. The choice between those two completely different ways of working, it all comes down to a single line. See this little parameter here? Arb, type, round robin? If it's set to 0, the arbiter plays by the strict priority rules. But if an engineer just changes that 0 to a 1, the entire system switches to the fair and square round robin method. Think about that. One tiny change totally redefines the flow of traffic. Yes, our packet got the green light. It's been granted access, and it is now officially cruising on the data superhighway. So what happens next? What's the journey like as it zips right through the core of the system? Okay, so sometimes, even on the express lane, you have to wait a little. This is where something called a FIFO buffer comes in. FIFO just stands for first in, first out, and you can think of it as a digital waiting room. Packets line up in this perfect orderly queue, and the system makes absolutely sure that the first one that got there is the first one to leave. No cutting in line allowed. But wait, how does the packet even know where it's supposed to go? Well, every single packet carries a header, which you can see in the code as TLPHDR. This is basically its shipping label, and it has everything the system needs to know. The requester ID answers who sent me, the tag is its unique tracking number, the address says where am I going, and the length tells the system how big of a package am I. Now, with all these packets zipping around, all these requests and confirmations, you might be wondering, how does the system even keep track of what it's supposed to be doing at any given moment? Well, it knows the answer thanks to something really cool called a state machine. See, the system has this special little notepad, a register called state_reg, that keeps track of its current status. If that register says REQ state idle, it means exactly what it sounds like. The system is idle. It's just hanging out, patiently waiting for the next packet to come along and make a request. The superhighway is totally clear. But if that very same state reg register is set to TLP state transfer, well, now we're in motion. The system is busy, it's actively moving a data packet, maybe it's our hero packet, down the data path. The superhighway is occupied, a delivery is in progress. Okay, so our packet has traveled the highway, it's reached its destination, but the journey's not quite over yet. There is one final, absolutely critical step. We've got to confirm the delivery was a success and, handle anything that might have gone wrong along the way. As soon as that packet is successfully delivered to memory, the system sends a confirmation message right back to where it came from. We can see this happening in the code with all these different status signals. It's literally the digital version of getting that your package has been delivered notification on your phone. The job is done and it's been verified. But what happens if something goes wrong? This is where the design is just so smart. It has built-in error handling. The code actually defines a whole bunch of potential problems it can look for. For instance, it can flag a DMA error timeout if a transfer is taking way too long, or maybe a DMA error parity if the data itself got scrambled in transit. The point is, the system isn't just designed to work, it's designed to fail gracefully. So we've been following the microscopic journey of one packet of data. Now it's time to zoom all the way out and really understand why this incredibly complex, totally invisible dance is so important for literally everything you do on your computer. Here's the part that's just truly mind-boggling. This whole journey we just walked through, from the request to the traffic cop's decision, the transfer, and that final confirmation, it doesn't just happen once in a while. It happens millions, sometimes even billions of times, every single second. It's just insane. And the amount of data this logic is built to handle is just staggering. If you dig into the parameters, you'll find a line that says DMA address width equals 64. What on earth does that mean? It means this controller is designed to manage a 64-bit address space. That comes out to 16 exabytes of data. That's an almost unimaginable amount of information. And this logic is engineered to navigate all of it. So, at the end of the day, why does any of this matter to you? Well, because this invisible, lightning-fast logic is the secret engine behind modern computing. It is the reason your games can load these enormous, detailed worlds without a hitch. It's why you can stream a 4K movie without it buffering. Ultimately, it's what makes your computer feel fast and responsive. Every time you use a piece of tech, you are relying on millions of these tiny, perfectly choreographed journeys happening in the background. So the next time you launch an app or load a web page, maybe just take a second to think about the digital superhighways humming away just beneath the surface. And it kind of leaves you wondering, doesn't it? What other invisible logic is out there powering your world?